Look back to the early formation of the universe, and it has been doing just that. It has taken pictures of 6 galaxies that are some of the oldest we've seen. But they're a little faded. This moment will take us back to the very beginnings of the universe. The announcement from the James Webb Space Telescope, JWST, regarding what lies at the end of the observable universe has sparked unprecedented excitement and curiosity. When the JWST was launched, its mission was clear: to peer deeper into space than any telescope before, unraveling the mysteries of the universe's origin, structure, and perhaps even its ultimate fate. This momentous occasion, when the telescope revealed its findings about the farthest reaches of the cosmos, marked a turning point in our understanding of the universe. For centuries, humanity has wondered about what lies beyond the stars, and now we have been given the most detailed glimpse yet into the distant frontier of space. Before we dive into the details, don't forget to hit the like and subscribe buttons for more exclusive news. The observable universe is a mind-bogglingly vast region, stretching approximately 93 billion light-years in diameter. It is the portion of the universe that we can see from Earth, limited by the speed of light and the age of the universe. As we look further into space, we are essentially looking back in time, since the light we observe from distant objects takes billions of years to reach us. The James Webb Space Telescope was designed to study these distant objects, operating in infrared wavelengths to penetrate cosmic dust and reveal ancient stars and galaxies. When the announcement came that the JWST had successfully captured data from the farthest reaches of the observable universe, it was a moment of profound significance. At the edge of the observable universe, the JWST discovered galaxies that existed when the universe was only a few hundred million years old. These galaxies are faint and distant, but their light has traveled billions of years to reach us. Their discovery represents a window into the infancy of the universe, allowing scientists to study how the first galaxies formed and evolved. The findings suggest that even in the earliest epochs of cosmic history, galaxies were forming more rapidly and in greater numbers than previously thought. This challenges existing models of galaxy formation and indicates that the early universe was far more dynamic than anyone had anticipated. One of the most fascinating aspects of these galaxies is their redshift, which refers to how much the light from an object has been stretched as it travels through the expanding universe. The higher the redshift, the farther away and, thus, the older the object is. The JWST's ability to detect galaxies with extremely high redshifts means that we are now able to observe light that was emitted shortly after the Big Bang. These galaxies, located near the edge of the observable universe, provide crucial information about the early stages of cosmic evolution. As we study these ancient structures, we gain insights into how matter began to coalesce into stars and galaxies, eventually leading to the formation of the complex universe we inhabit today. The implications of these discoveries are profound. By observing the end of the observable universe, we are essentially witnessing the universe's childhood. This era, known as the Cosmic Dawn, is a period that has long eluded detailed study due to the limitations of previous telescopes. The James Webb Space Telescope, with its advanced capabilities, is now able to shed light, both literally and figuratively, on this mysterious time in cosmic history. The galaxies detected at the edge of the observable universe are not just relics of the past. They are also key to understanding the processes that led to the formation of larger structures like galaxy clusters, superclusters, and ultimately, the large-scale structure of the universe itself. In addition to providing new insights into the formation of galaxies, the JWST's findings also raise questions about the nature of dark matter and dark energy. These two mysterious components make up the vast majority of the universe, yet they remain poorly understood. The data collected from the end of the observable universe may offer clues about how dark matter influenced the early growth of galaxies and how dark energy has driven the expansion of the universe. The universe, just a few hundred million years old, a mere fraction of its current age of 13.8 billion years, was in its infancy when these primordial galaxies were formed. These galaxies, faint and redshifted by the expansion of the universe, offer a unique window into the earliest stages of cosmic evolution. Prior to the James Webb Space Telescope, astronomers relied heavily on the Hubble Space Telescope, which gave us incredible insights into the universe. However, its capabilities were limited in terms of observing the very first galaxies and stars. The Webb telescope's ability to detect infrared light, which is stretched by the expansion of the universe, allowed it to look further back in time than ever before, capturing images and data from a time when the universe was only 3 billion years old, or even less. What the JWST saw at the end of the observable universe wasn't just a few faint specks of light. It was the formation of the very first galaxies, possibly even some of the first stars, known as population 3 stars. These stars, made entirely of hydrogen and helium, are thought to have been massive and short-lived, burning through their nuclear fuel quickly before exploding in supernovae that seeded the cosmos with heavier elements necessary for the formation of planets, life, and everything we know today. Observing these ancient stars and galaxies is critical because it helps us understand the processes that led to the development of the complex universe we inhabit now. The discovery of these ancient galaxies also raises profound questions about the structure and limits of the universe. When we talk about the end of the observable universe, it's essential to realize that it's not a physical boundary. Instead, it marks the furthest point we can see due to the finite speed of light and the expansion of the universe. Beyond this horizon, the universe likely continues, but we have no way of seeing it because the light from that distant region hasn't had enough time to reach us. The JWST's ability to push the limits of our observable universe even further opens new possibilities for understanding what lies beyond that horizon. One of the most tantalizing implications of this announcement is the insight it provides into the expansion of the universe itself. The universe has been expanding since the Big Bang, and this expansion appears to be accelerating due to a mysterious force known as dark energy. By studying galaxies at the edge of the observable universe, the JWST helps astronomers measure the rate of expansion more accurately, shedding light on the nature of dark energy and how it might evolve in the future. This has profound implications for the ultimate fate of the universe. Will the universe continue to expand forever, with galaxies drifting further and further apart until the stars burn out and space becomes a cold, dark void? Or could dark energy change over time, perhaps causing the universe to collapse back in on itself in a big crunch? These are the kinds of questions that the data from the JWST will help answer. Moreover, the JWST's findings at the edge of the observable universe force us to reconsider our understanding of cosmology, particularly the idea of inflation. The rapid expansion of the universe in the moments after the Big Bang, known as inflation, suggests that the universe expanded exponentially in the first fractions of a second, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. However, if the JWST finds unexpected structures or anomalies in these distant galaxies, it could challenge the inflationary model, prompting physicists to refine or even overhaul our current understanding of the universe's earliest moments. Beyond the cosmological implications, the announcement has philosophical and existential significance as well. The discovery of galaxies at the farthest reaches of the observable universe prompts us to ask fundamental questions about our place in the cosmos. What lies beyond the observable universe? Is there a multiverse with countless other universes existing beyond our own, each with its own set of physical laws and conditions? Some theories suggest that the observable universe is just one bubble in a vast multiverse, with other bubbles existing beyond the cosmic horizon. If true, this would mean that the universe we see is only a tiny part of a much larger and more complex reality. These discoveries also highlight the limits of human knowledge and the scale of the universe. As we look deeper into space, we are reminded of how small and fragile our planet is in the grand scheme of things. Yet, at the same time, the fact that we are able to observe and understand the universe to this degree is a testament to the power of human curiosity and ingenuity. The James Webb Space Telescope represents the pinnacle of decades of scientific and engineering effort, and its discoveries will shape our understanding of the cosmos for generations to come. In addition to expanding our understanding of the universe's origins, the JWST's observations at the end of the observable universe will likely have practical implications for the search for extraterrestrial life. By studying the first galaxies and stars, astronomers can gain insights into how the conditions necessary for life, such as the presence of heavy elements like carbon and oxygen, developed over time. This, in turn, informs our understanding of where life might exist elsewhere in the universe. While the stars and galaxies at the edge of the observable universe are too far away for us to detect signs of life directly, Studying their formation can help us understand how common life-bearing planets might be in other parts of the universe. The announcement also underscores the importance of collaboration and international cooperation in advancing our knowledge of the universe. The JWST is a joint project of NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, and its success is a testament to the power of global collaboration. No single country or organization could have built and operated a telescope as complex and advanced as the JWST on its own. The telescope's discoveries, including its observations at the edge of the observable universe, are the result of the combined efforts of thousands of scientists, engineers, and technicians from around the world. The James Webb Space Telescope's revelation of the most distant reaches of the observable universe does more than merely extend the boundaries of what we can see. It fundamentally challenges and reframes some of the most long-held assumptions in cosmology, astrophysics, and even philosophy. To grasp the full depth of what the telescope's observations mean, we must delve into the intricate and often bewildering details of how the observable universe works, what the telescope has shown us, and how those revelations change our understanding of not only space but time, existence, and the laws that govern them. One of the most profound implications of the James Webb Space Telescope's announcement is its potential to refine or redefine the standard model of cosmology. The standard model describes the universe's expansion from the Big Bang, around 13.8 billion years ago, to the present day. Embedded within this model are assumptions about how matter and energy behave at vast scales, about the early universe's rapid expansion through inflation, and about the mysterious dark matter and dark energy that seem to make up the majority of the cosmos. The discoveries made by the JWST at the edge of the observable universe could force us to rethink these assumptions. The first stars and galaxies, those early structures captured by the JWST, are unlike anything we observe in the local universe. They are more massive, and their formation times may be much earlier than previously expected. These findings could indicate that the models we use to describe how galaxies form from clouds of gas might need adjustment. The standard model suggests a certain time frame within which galaxies form, based on the cooling of gas and the clustering of dark matter halos. If the JWST is observing galaxies far older than this model allows, cosmologists may need to reconsider the exact processes that drove early galaxy formation. There are also more speculative theories about the universe that this discovery touches upon. For instance, there's the idea that the universe is a hologram. The holographic principle suggests that the entire universe can be described by information encoded on a two-dimensional surface at the boundary of the universe, similar to how a hologram encodes a three-dimensional image on a two-dimensional surface. This hypothesis comes from attempts to reconcile quantum mechanics and general relativity, particularly in the context of black holes. While this theory is far from proven, discoveries that extend our understanding of the universe's outermost regions inevitably feed back into these theoretical frameworks. Perhaps what we think of as the end of the observable universe is not an edge, but a form of boundary where different physical laws or interpretations of space and time come into play. The JWST's revelations about what lies at the limits of the observable universe also intersect with debates about the nature of time. In Einstein's theory of general relativity, space and time are intimately connected, forming a four-dimensional fabric known as space-time. The telescope's ability to look so far back into the universe's history means we are also looking into deep time, when conditions were radically different from the present. One of the more fascinating aspects of the James Webb Space Telescope's discovery is how it impacts our understanding of the early universe's timeline. The early universe was filled with a hot, dense plasma in which atoms had not yet formed. As the universe expanded and cooled, it reached a point known as recombination, where electrons combined with protons to form neutral hydrogen, allowing light to travel freely for the first time. This event, known as the cosmic microwave background (CMB), is considered the furthest point back in time we can observe. However, the galaxies the JWST has observed date to a time shortly after this era, during the epoch of reionization, when the first stars began to ionize the hydrogen that filled the universe. Understanding what happened at the edge of the observable universe offers insights into this period, and reconstructing a timeline of cosmic events could fill the gap between the CMB and the formation of the first stars. This means more than just discovering old galaxies. It's about reconstructing a timeline of cosmic events. The discovery of ancient galaxies raises critical questions about the dark ages of the universe, the period between the release of the CMB and the formation of the first stars. This gap in our understanding could be filled by JWST observations, revealing how and when light first broke through the dark veil of the early cosmos. There's another profound consequence of Webb's new data. It adds a critical layer to our understanding of dark matter and dark energy. These mysterious substances are thought to constitute about 95% of the universe's total mass energy content. Yet they do not interact with light, making them undetectable by conventional telescopes. Dark matter is believed to form the scaffolding around which galaxies coalesce, while dark energy is driving the accelerating expansion of the universe. By studying the most distant galaxies, the JWST can provide indirect evidence of how dark matter influenced early cosmic structure. More importantly, by measuring the universe's rate of expansion at different times, it will help refine our understanding of dark energy and its role in the future evolution of the cosmos. The end of the observable universe may offer some of the best clues yet about these invisible forces shaping everything we see. Additionally, the JWST discovery forces a reevaluation of how we define the boundaries of the universe itself. The notion of the observable universe is based on the distance light has traveled since the Big Bang, but the actual universe beyond what we can observe could be far larger, perhaps even infinite. One concept that has gained traction in recent years is that of the multiverse. In this view, our universe is just one of many, each with its own physical laws and constants. These universes might exist in separate regions of space or in parallel dimensions that we cannot detect. The observable universe could be just a small bubble in a much larger multiverse, and what we see at its edge could be a tantalizing hint of other universes beyond. Moreover, the revelations of JWST push the boundaries of our technological imagination. The telescope operates at the very cutting edge of what human engineering can achieve, utilizing a sun shield the size of a tennis court and mirrors made of beryllium, coated in a layer of gold to reflect infrared light. The extreme precision required to align these mirrors and control the telescope from 1,000,000 miles away is a feat that highlights humanity's capacity for innovation. As we marvel at the distant galaxies the JWST has revealed, it's worth reflecting on the incredible technological journey that brought us to this point, from Galileo's first crude telescopes to this sophisticated marvel of modern science.